Hello, this is Jack Hicks, and this is my lab report for the second lab in Physics 2211, projectile motion. So the objective of the lab was to observe, record, and analyze the motion of an object that is thrown and moves like a projectile, and then to create computational models based on the observed data and physics principles that predicts the motion of the object when affected by either gravity or gravity and the drag force. And then doing both of those, we could compare the computational models and the observations by plotting all the data values on the same graph. So the main ideas in play here were Newton's first and second law. Newton's first law saying that an object in motion stays in motion unless acted upon by an outside force, in this experiment being gravity and drag. And Newton's second law, which says that an object's change in velocity is determined by the amount of force applied divided by the mass of the object multiplied by the change in time. So this experiment, we had to take into account the force of gravity, which is negative mg, m being mass, gravity being a constant, 9.8 meters per second, and this is due to the Earth, and then drag, which is negative bv squared. Keep in mind that these are both magnitudes. The directions come into play later. Um, and drag is a force opposite in the direction of motion due to resistance by air particles. And then B is just a proportionality constant, which was found by matching up experimental uh, and observed data. And so we know that the net force is change of momentum over change in time. So if we apply this force, divide it by mass and times time, we can get our change in velocity. And then using that final velocity, multiply that by the change in time, we can get our change in position. In this experiment, the system was the ball of paper, which was thrown to the left, which we have denoted to be the negative x direction, and the surroundings, which were the air, the earth, and pretty much everything except the ball of paper. And a little preview was that by comparing the experimental results with the computational models, it was found that the model that didn't include the drag force traveled furthest in the negative x direction, and the observed trajectory achieved the highest y value. And GlowScript was used to do the coding because it made for easy and efficient computations. So what models are we using? So the model we used was Newton's second law using GlowScript and the Lab 2 starter code, which was a while loop to continuously update the force, velocity, and then position of the object over specified time intervals. One of our models only updated the force with the force of gravity, whereas the other updated them with the force of gravity plus the force of drag, which we explained earlier what those were. And you can see the equations down there that we used in our models. Now, the known values, both observed and in our models, were the mass of the paper ball shown there, the initial velocity shown there, and the initial position also shown on the right. So getting into the actual experiment, here's a video of me throwing the paper ball.
Yeah.
Here's the tracker data showing the calibration stick, the axes, and the individual data points, and the x position versus time and the y position versus time. So then we take this data and make predictions about the motion we just observed using GlowScript. So here's the GlowScript code for the model without drag using the velocity, force, and position update formula as we described earlier. The highlighted parts being the important parts, the mass of the ball, the position, the velocity, the B value, which in this case is 0 because there's no drag, and then the force, the velocity, and the position being updated in the while loop. And as you can see, the force here includes both gravity and drag, but the drag is 0 because of the 0 B value. And this is the code for the computational model with drag, which is the exact same as before, except the B value is now not 0, and it was experimentally determined by seeing which B value would match up our final positions to that of the observed values. Here you can see the results gained from the computational model not including drag. The velocity will be touched upon later, but the position versus time, the x and y values are in accordance with a standard projectile motion model. Here are the results with the model including drag, and as you can see, it's very similar as before, except some of the velocities are different and the position is also slightly different. It should also be noted that the drag arrow is not shown just simply because it is so small, but it is there. Now let's compare these data sets. Looking at all three sets of data, it can be shown that they all start at the same place. However, the observed data set attains the highest y value, whereas the model without drag goes the furthest in the negative x direction. And the model that includes drag and the observed data both end at roughly the same x and y values. And the observed model is the least smooth, probably because of other forces that aren't accounted for. It should also be known that there could be error due to incorrect plotting of tracker data points and a non-exact b-value and unaccounted forces like gusts of air. So some additional questions would be, what if the object was thrown straight up with the same velocity? Well, it would reach the ground at the same time, because as the equations show below, the y components are not affected by the x components. Now, do any of the models predict terminal velocity? No, because none of them have a net force of 0, but you could do this by dropping something from a very high position so that it reached terminal velocity.